In the last video, we started talking about Markov models as a way to model temporal data using the fact that in the real world, the future is independent of the past given the present. And in this video, we're going to see how this sort of idea is formulated mathematically in the simplest type of Markov model, what's called a discrete-time Markov chain. So we'll make two simplifying assumptions in addition to the basic Markov assumption. Simplifying assumptions. We'll assume discrete time, which we were sort of already assuming, and discrete, if I can write here, discrete space. And by space, here I mean the set that the random variables xi take values in. So xi will be a discrete random variable. And by discrete time, we mean that, here if we're thinking of these as units of time, t equals 1, t equals 2, and so on, that time occurs at discrete intervals rather than continuous. You can actually have what in generalization called continuous time Markov processes. You can actually have a function, a random function, or this would be time, and this would be, the value of the function. And so the random variable xt is actually a continuous function. Or it could be discontinuous function, but it takes a value at every single real valued number t. Okay, but so under these simplifying assumptions, we have the definition, the classic case. So we'll say discrete random variables x1 to xn form a Markov, let me say a discrete time Markov chain. We'll emphasize the discrete time. Usually when people just say a Markov chain, they mean a discrete time Markov chain, but let's emphasize that. If their joint distribution respects the graph, the following graph, x1, if it respects the following graphical model, x2, I'll write one more so the pattern's clear, and so on. So it's a directed graph that's a chain. Hence, a Markov chain. Oh, yeah, there it is, right. I did write Markov chain. I thought I skipped Markov chain. So these discrete random variables form a discrete time Markov chain if they respect this, if their distribution factors according to this graphical model. Or in other words, another way we could say this is that the joint distribution, or not the joint distribution, but the probability of xt given all the previous values of x1 up to xt minus 1, equals the probability of xt given xt minus 1. In other words, xt is conditionally independent of x1, 2, 3, 4, up to xt minus 2, given xt minus 1. And these two are equivalent. So let's check that they're equivalent, actually. Let's check that. So let's say we'll take t to be 3, for example. And we'd like to say that x3 is conditionally independent. So let's assume that we have this graphical model, that it respects this graphical model, and let's see if this statement applies. So we'd like to say, to prove this statement, that x3 is conditionally independent of x1 given x2. And that's true by the d-separation property. So if we condition on x2, then by the d-separation property, every path from x3 to x1 passes through x2, and this is a tail-to-head relationship. And therefore, it's conditionally independent. So from this direction to this direction works. And the same thing would work, for any other one. And so now let's check from this direction, from this to this. So if we have this sort of conditional independent statement, does that imply that the x1 through xn respect this graph? Well, what does it mean for them to respect this graph? Let's write down what that means. That means that the joint distribution on x1 to xn factors as the probability of x1 times the probability of x2 given x1, right? So we have a product over factors, or we're going to have one factor for each node in each random variable in the graph, and then conditioned on its parent. So it's the probability of x2 given x1, probability of x3 given x2, and so on, probability of 4 given x3, up to the probability of xn given xn minus 1. And in order to show that this implies that this respects this graph, we need to show that this implies that the joint distribution satisfies this factorization. And so another way to factor this would be probability of x1. In general, we can always factor a joint distribution as probability of x1, so we want to prove this. We can always factor as probability of x1 given probability of x1 times the probability of x2 given x1 times the probability of x3 given x1 and x2, and so on up to probability of xn given 1 up to n minus 1. We can always do this. And now this is exactly the condition that we need to make these equivalent, right? Well, of course, this one's equivalent to this, and that's equal to that. And to match these two up, this is exactly what we need. And so on for each of the others. So this implies that these factors are equal, and therefore that's a check. So therefore, these x's respect these discrete random variables x1 through xn respect this graphical model. So these two statements are equivalent. And there are a number of other equivalent ways to characterize this type of model, but these are sort of the most common. And this is always the nice sort of picture to keep in your head for a Markov chain, this graphical model. Okay, so that was the case, right? So in our little discussion to motivate this definition, we talked about that xt could depend also on the previous m random variables, and we were just thinking about the simplest case. This was just the simplest case where m was 1. And so, more generally, you could have the following. You could have, let me just, rather than draw all the x1, so that would be x1, x2, x3, x4, x5, x6, x7. So we had this sort of thing. And to have, in the generative model, to have x3 also depend on x1, we would need a link here. And to have this one, so have 4 depend on 3 and 2 in the generative process, we would need to have this link. And so on. And this is what's called a second order Markov chain, if they're discrete random variables and all. So by contrast, sometimes people refer to this as a first order discrete-time Markov chain. And of course you can go on, you can have third order, third order would be another link here, and so on. So that's one sort of generalization that you can make from this. Another generalization, something I alluded to earlier, is you can have continuous time Markov chains or Markov processes. And that was this thing I sort of talked about before, where it could be a function. So an example of a continuous time Markov chain or Markov process is Brownian motion. And actually that's a, well, maybe a simpler example would be a Poisson process. This is time, and this is the value of a random variable. And at real valued times, at exponentially distributed intervals, this jumps. It always takes integer values. So that's a Poisson process. That's a continuous time Markov chain. And another generalization would be a continuous, you could have continuous space. A Markov process. So I'm saying Markov process is a little bit more, usually when we say process, we also allow for continuous time rather than Markov chain to sort of indicate discrete time. But a continuous space example, a generalization, would be, well, sometimes these are referred to as state space models. State space. And like I sort of mentioned, maybe I'll just draw one example, a 1D example. Brownian motion in one dimension. Looks something like this. It's extremely jagged, so this would be time. And you could imagine, when you look at this, you might immediately think, well, that looks kind of like a stock price. And in fact, people do use these continuous time Markov chains to model stock prices. Brownian motion. And in fact, Einstein used Brownian motion, or he analyzed Brownian motion in one of his early papers in 1905. So Brownian motion in 2D, so this would be 1D, this would be 2D, to model a randomly moving particle, like a particle of pollen in a glass of water. So those are some generalizations. And let me just give you a concrete example here of a discrete time, a discrete space, discrete time, random, a discrete space, discrete time first order Markov chain. An example would be, so let me put it down here. Example, so these are generalizations. And here's an example. One example would be, so it sort of looks like these. A random walk on the integers. So you have integers 1, 2, 3, minus 1, minus 2, minus 3, and 0 here. You start out at 0. This is time. And then at each unit of time, 1, 2, 3, 4, 5, and so on, you either increase, so you increase by 1, so xt is going along this axis. Xt increases by 1 with probability 1/2, and it decreases by 1 with probability 1/2. So maybe, if we were to sample from this, maybe it would go up and then down again, and then up and up and up and up, down, up, up, so on. And this is called a random walk. Discrete time and discrete space. And so you can sort of see how this is a simplification of this 1D Brownian motion. That's one example. And so in the next video, we're going to start to look at well, let me stop here and give you maybe one more example of a Markov chain, a discrete time, discrete space Markov chain, and then we'll start to analyze the limitations of this, and that will lead us to hidden Markov models.